a view-dependent terrain rendering algorithm, whose performance and memory usage is independent of the terrain size, and which is all very short and simple. First, let's show it a little bit. Then it will be introduced a little bit more in detail. This new algorithm is complete of the features needed for providing dynamic level of detail, using the triangulation scheme pioneered by Peter Lindstrom and co-operators 1996, later investigated further by Peter Lindstrom himself together with Valerio Pascucci 2002. My new algorithm is closer to the last one, but keeps only the idea behind that, while it is a completely newly conceived algorithm I developed from zero, in the attempt to create an algorithm which arrives at the same result, but using much less memory and being short and simple. Said very roughly, the main idea behind this algorithm is that either we want a view-dependent decision of what detail is included in the triangulated surface, either we just use some rough criteria like putting smaller blocks near the camera and bigger blocks further from it. It is still dynamic level of detail. The view-dependent thing is certainly better, but the idea is that the main purpose is not to provide each instant, like 30 frames per second, all and only the details actually visible from the current point of view with a given perspectivic projection of points to screen, but rather to gradually vary the detail in a way to arrive quickly at the right amount of detail in the right sides of the terrain as the camera moves around, or at least to approach the ideally right detail. Let's state it in another way. What we want is an algorithm which provides most of the relevant detail by the time we get close to the site we want to inspect and while we approach it. The detail must change quickly, but must not necessarily be always the ideal set of details visible. It's sufficient for it to contain most of the relevant stuff. This algorithm exploits as much as possible this idea of dynamic level of detail to do a good job in a simple and very fast way. That is, to always progressively approach the ideally right level of detail, where progressively means that it does little change at a time, but in a context in which those little changes, if iterated many times, allow to reach any configuration of how detail is distributed across the terrain being rendered. The basic functionalities for providing dynamic level of detail as it is implemented in this algorithm provides essentially the language for expressing and implementing the advanced features which provide view-dependent, continuous, dynamic level of detail. View-dependent, continuous level of detail system simply means that ideally it is able to provide completely seamless transition of level of detail as it is seen by the observer. I mean, no pop-up of detail and such visual artifacts. This because the level of detail to which the transition can be determined exactly. So, continuous level of detail is usually a synonym of advanced industrial quality methods. In order to understand clearly and precisely the advanced features which make difference between a generic dynamic level of detail system and a view-dependent continuous level of detail system, we need to understand the way this algorithm implements, or let's say approaches, the problem of dynamic level of detail. Let's get started. 3, 2, 1. Let's explain it simply and concretely. The whole procedure is a conceptually endless repetition of a single program cycle, as indicated in the figure. This is a program cycle. According to how the dynamic level of detail is implemented in this algorithm, at each cycle there exists a configuration, a set of blocks covering a square area. And there is absolutely no such a thing as a record of what there used to be in the cycle before and what there is going to be after. What exists is a current block set. Thus, we have a vector containing our blocks. At the very beginning, when the program is started, and we are here, according to the score system, there exists one big block covering the whole square area, which is our terrain. This is block 0. So, our vector ends here. Now, if we want to change the level of detail somewhere, let's think of it as the attempt to include in the mesh some point, as much as really including it is possible, because we think that that point contributes some significant information. So, our point is here, for example. And in the cycle, which we have introduced before, there's a little procedure which checks if this point is within the area of any of the currently existing blocks. And if this test is positive, this block is replaced with its 4 children blocks. And so, the parent block exists no more. As we have added its 4 children, this one, the parent, is deleted. And we are here. We have arrived at the end of the cycle, and it starts again. Now, all what exists in our rendering, just forget about what there used to be before. There are 4 blocks in the vector. And there are these 4 blocks. Fine. We want to assure that the point about which we have been speaking before is included in the mesh. And so, since these 4 blocks exist, each of these is checked for matching the area. Is the point within the area of block 1? Yes. Then for the others, negative, negative, negative. Then this block, block 1, is taken and is replaced by its 4 children. And the parent block is deleted forever. And so on. And at some point we reach the last level, and then the blocks are not divided anymore because we put a limit, for example, on how small a block can be in the extreme case, or because the point falls exactly on one of the corners of an existing block. Very fine. This is the concept of dynamic level of detail as it is implemented here in this algorithm. And of course, as we could include one point in the mesh by narrowing progressively the block set to include that point, so we could include more points. We just have to do this check for more points and schedule the blocks which need to be replaced by their 4 children, and then replace them. Adding detail is fine, but also subtracting detail is needed. The principle is similar, but a bit more tricky. Essentially, if there are 4 sibling blocks, we can replace them with their parent block. But since there are not sibling blocks everywhere, subtracting detail is not possible everywhere, even if it is always possible at least in one place. While it always makes sense to add details somewhere in the block set, it only makes sense to subtract detail from wherever there occur 4 sibling blocks. We can subtract detail from there. To make it more clear, it also makes sense, for example, to brutally subtract detail from wherever possible, and reiterating this operation enough many times would lead to have one big block present. Combining a stage of detail addition and a stage of detail subtraction, we can create a dynamic balance of detail addition and subtraction. Thanks to this, we can quickly arrive at any configuration, or let's say block set, in an efficient way. Detail subtraction is a bit more delicate than addition of detail, as the very balance between the two operations itself. In fact, quadruplets of blocks, that is, 4 sibling blocks, occur always somewhere, but not only in areas where a detail addition has just occurred. If done inadvertently, it may accidentally happen to subtract detail from all those areas, so cancelling the effect of the detail addition previously done. According to this, for simplicity, let's assume we subtract detail from everywhere it is possible except in a circular area within which the camera is assumed to stay. To make this more practical, let's assume also that the radius of this circular area is nearly half of the height at which the camera is placed, place from which the camera looks tangentially downwards. 3, 2, 1. So far, anyway, this only produces a coverage of the surface, which has no particular qualities. It is a bit too primitive yet, because it's hard to really define in it a level of detail near some area, since there can be 2 areas next to each other which are covered by blocks of very different sizes. While instead it would be nice, and soon we introduce why it is necessary for most practical needs, to have a coverage in which blocks next to each other can have maximum 1 level of difference, that is, to have sides either equally long as the nearby one, or twice as long, or half as long. That's all. If you have any doubts, think to a single point being dragged around the area of the terrain, as described before. The details vanish progressively outside the circular area. To generalize it, think that there be more points around which to narrow detail, and that's all. Fine. We have introduced the way dynamic level of detail is implemented in our algorithm. Let's refine the thing a bit. That's how our algorithm concretizes the concept of dynamic level of detail. Let's see the cycle. Insert figure or text overlay outlining the algorithm here. This, repeated enough many times, produces a nice, that is progressive, featuring maximum one level of difference between blocks next to each other, coverage of the same square area, varying over time. Same area covered, but practically always covered in a different way. That's it for now. If also stage 4 is implemented, this varying coverage is correctly applied to a Hilda surface. It will be a polygonal, triangulated to be more precise, approximation of a surface, fully connected and without holes. So it will be fine, but it won't be aesthetically any big deal, nor will it produce a really meaningful approximation, or let's say representation or whatever, of the surface. If instead of choosing randomly at which blocks to give more detail, we rather add detail to a block within whose area a point x epsilon falls, then we obtain already something more meaningful, more detailed approximation of the surface near the point, and progressively more rough approximation further from it. We just have to add to this the little tuning mentioned some paragraphs before, according to which we won't remove detail from those areas which fall within a circular area, abundantly including the camera looking at part of the area. We could tune this rule further to obtain a reasonably good rendering of the surface, but the purpose of this explanation is to introduce to a rule which produces industrial quality rendering of the surface, which is deterring in this context. The refinements to this core algorithm take care of choosing the detail to add and to subtract in a way to produce a good approximation of the surface as it is seen from a given camera shot with a given screen resolution. These refinements are introduced in the part dedicated to advanced topics, as much as it can fit into this provisory video. The advanced features. View-dependent evaluation of the most significant details. The view-dependent decision of what details to add and to subtract from time to time seamlessly fits into the algorithm so far as we introduced it. Let's get started. Step 1 and Step 2 of the previously outlined cycle are modified, as simple as that. For the rest, it's the same, ideally endlessly repeated cycle, but in which stage 1 and stage 2 are a bit different. Let's present the modified cycle. At the beginning of it, we have a block set in which blocks occurring side by side can have maximum one level of difference. This is because, according to the way a block can be triangulated, it's possible to produce a fully connected triangulation, which, said in other words, is free of T-junctions. Just look at the scheme and some examples to understand it fully. Let's present stage 1 and stage 2 in their new view-dependent fashion. As regards stage 1, said very roughly, a block is replaced with its 4 children if any of them contributes some significant detail from the current point of view with the current perspectivic projection, and of course the screen resolution. Instead, as regards step 2, similarly to step 1, 4 sibling blocks are removed and replaced with their parent block if none of them contributes any significant detail. As you can see, as in the, let's say, naive versions of step 1 and step 2, of course, maximum one level of additional difference can happen to be added, so a maximum of 2 levels of difference can accumulate. So it's fine. Step 1 and step 2, of course, can be inverted in their order if you are more comfortable. So since step 2 doesn't create any level differences, inverting the 2 tasks can ease the understanding of the overall procedure. Then comes stage 3, which adds some blocks here and there to bring down to 1 any level differences equal to 2 in blocks occurring side by side. Then comes stage 4, which triangulates the blocks in a way to create a fully connected triangulated surface. That is, said in other words, a triangulated coverage of our square area which has no T-junctions. Look at some examples to understand it better. This is the end of the cycle. Stage 1 could schedule addition of points in the triangulation of a block to make sure that really all points with a sigma different from 0 are included in the triangulation. But this option is not discussed in this video. In fact, the rule, as simply as we stated it, works perfectly fine since stage 3 and stage 4 together produce a block set in which blocks most of the times are triangulated in a way which includes most of their points, and so it's all fine. Regarding this, of course, in the industrial strength implementation, this little feature is implemented with a little bit of engineering to do it really well, without introducing complications and any compromission of the performance and of the determinism of the, let's say, worst case amount of operations needed for the algorithm to complete a cycle. Because yes, it's deterministic, which is a very strong quality indeed. The number of operations required to complete a cycle is roughly proportional, if not linearly, to the number of blocks present at the beginning of the cycle, anyway largely within the number of blocks present at the beginning of the cycle multiplied by the natural logarithm of the number of blocks present at the beginning of the cycle. And all this is a very good complexity in terms of operations or for an algorithm of this kind. Fine. This ends the introduction to the view-dependent thing. At this point, some closing comments are in place. We have only quickly mentioned stage 3 of the algorithm. In fact, discussing it well would need more space than this provisory video allows. Most of the heavy theoretical and practical research to establish this algorithm was focused on the feasibility of stage 3, in fact. And as a theorem, also an algorithm has consequences. Sometimes these are minor, sometimes instead the consequences outperform by large the very significance of the original theorem or algorithm itself. It's also our case, in fact, in the current algorithm only in stage 3 there is need to specify how, let's say, large the terrain is. which is to say how many height samples by how many height samples the height map is made of. But according to some further research I've done recently, there's the possibility to do also that with no such extra stuff. I mean, nothing more than what the block set says about the terrain. That would be, in fact, a way to use the algorithm to render terrains also in full streaming of the data about the height map. That simply means, in this context, that because of perspective, however big and detailed the height map is, no more than an overall maximum amount of detail can be seen, so no more than, say, 2000 blocks will ever be needed to do even an excellent rendering of the terrain. The idea of streaming height map data is that storing height map in memory is not even considered. That means that gigabytes, many gigabytes of geographic data stored in the form of a height map could be rendered by accessing the data only when needed. In fact, if you paid attention to stage 1 of our algorithm, is the only part where it just does some, let's say, query about new points of the height map which are not currently included in the triangulation proposed. As said, in a more practical way, if we could implement a stage 3 in a way that it does everything in this full streaming fashion, our rendering program could render many gigabytes of height map using just like 16 megabytes of memory while running. I hope we have given sufficiently strong background to allow you to easily understand these concepts. This ends the presentation. Thank you for watching. Hope you liked it. Now that we have introduced conceptually and strengthened with practical examples the way a square area is covered by our algorithm, as a final touch to make the theory coherent and really bulletproof, we can say something about the nature of the coverage achieved. You probably have noticed that although blocks are created and deleted as the algorithm goes on, each block somehow is unique. Even if it is created, deleted, and then recreated sometime, each block occupies the same area unique to it, having a unique center, for example. Let's elaborate shortly on this concept. If you imagine starting with one big block and then replace it with its children and then replace all those with their respective children and so forth, you arrive at a coverage of the area made of blocks all with the same size. And if you consider the passages made to arrive at this point, you realize that the blocks created and deleted over time, if we had kept record of each, would form a tree structure, more precisely a quadtree. Look carefully at the figure. Nodes of the quadtree have a unique number which identifies each univocally. This fact allows to give to each block a unique ID number, because blocks conceptually are nodes of this quadtree even if the tree is not stored, because the blocks are created and deleted as the algorithm goes on. This is very important because blocks which have smaller ID numbers are larger, and step 3 can be completed only if the vector which holds the blocks is sorted according to the ID number, so that we are sure to proceed from larger blocks to smaller blocks. This ends the outline of the algorithm. Now, some practical considerations are in place. The algorithm achieves easily 40 frames per second on a low-end computer, in which it manages to do exactly 10 updates of the level of detail. If it runs at 60 frames per second, it does 15 updates of the level of detail. Not as if 60 frames per second would be any big advantage over 30, since 30, 40 is perfectly fine. The algorithm, as it is implemented in the program, divides the cycle, which we have introduced some paragraphs before, into 4 different substages, which are the 4 key stages it is made of. This could be merged together to obtain better frequency of the update of the level of detail with the same frames per second achieved. But the division, as it is implemented in the program you see, is a good precaution to allow program to run well also on very low-end computers, and to leave lots of resources for the case in which this algorithm is used just as a sub-procedure in the context of a program which does many other things, such as it could be a video game or a 3D map program, etc. In fact, it's sufficient that the update of the level of detail is enough frequent for producing nearly flawless visual results. The industrial strength implementation of the algorithm supports, of course, dividing further the operations by dividing further each 4 stages into further stages. Said very roughly, there's a parameter which tells how many blocks can be operated at a time, and so each of the 4 stages, each of which of course needs to operate all blocks, is just limited to operate as many blocks at a time as specified by the parameter. This is useful in those cases in which, of course, the computer on which the program is running is not able to provide enough frequent updates of the level of detail to provide a view-dependent kind of rendering. Of course, this feature of being able to subdivide further the operations is instead very useful in those cases in which the program is sufficient to allow inspecting a large data set of geographic data, because thanks to things introduced among the advanced topics, but not introduced in this video, one can do a fairly good job by exploiting those topics. Okay, for this video it's sufficient here. That's all to say that the algorithm is very versatile and it can be adjusted for many needs.